Good evening. I'm Craig Reck, in for Megan Donaghy, who may or may not be locked in her dressing room right now. Anyway, we all understand the basic concept of climate. The sun provides the energy that warms the earth. Typically, temperatures are warmer in areas near the equator where the sun hits more directly, and cooler in areas towards the poles where the sun hits less directly. Makes sense, right? So why is it that St. John's in Newfoundland has an average temperature of 23 degrees Fahrenheit in the winter, but further north in London, England, the winters average about 34? It's the same case in Norway, where the winter lows average 34, but over in Moscow, which is on the same latitude, winter lows average 16. What's up with that? It's not a typo, and it's not a faulty thermometer. What you're seeing is a phenomenon caused in part by the transfer of energy by ocean currents, in this case the Gulf Stream, and a big cycle which I'm guessing has an equally big name. All this and more after the break. Yeah. Most people have, at the very least, heard of ocean currents and know that it involves the movement of ocean water. But many don't realize the tremendous effect that currents can have on climate. And today, we're going to find out just how that works. We're here with Mark Lucas, professor in the Department of Physics and Astronomy at Ohio University. Wow, Mark, I gotta say, it's a pretty impressive set here. Do all scientists get their own TV set?
Oh, it's a little-known perk.
Well, it looks like your aquarium here is a little short on fish.
This is really an experiment that's going to help us see what drives these ocean currents. I have this fish tank filled with water, but no fish. I have this cup of warm water, and I have this cup. Don't drink that!
Why? What's wrong?
We put phosphorescent dye in the cups. You don't want to go around gulping this stuff.
I thought it was Kool-Aid.
Do you always drink things you see lying around?
I do when it's Kool-Aid.
Fortunately, we have the second cup here. All right. I'm going to turn on the black light. Unbelievable. Okay, without drinking, we're going to put the cups over here.
Okay.
And poke a hole in the side. I'm going to put the cup under the water.
Okay.
And pull out the skewer.
Okay. So, Mark, aside from, making a big mess, what did we just do?
Well, you see over here, the hot water is staying near the top.
Mm-hmm.
That means it's less dense than the water that's in the tank, so it floats to the top. The cold water, as we can see over here, is sinking towards the bottom. That means it's more dense.
Oh. Cool. So can I drink the water now?
No. Come on over here.
Getting deja vu here, Mark.
So we have a little puzzle for you, all right? We have 2 cups of water.
Mm-hmm.
We have a tank filled with water. We're going to do the same thing. We're going to pull these cups up. We're going to poke holes in them. We're going to see what happens.
Let's say I'm a pro by now.
There we go.
All right. And they're off.
So why does that happen?
Well, I'm guessing the water in your cup is colder, making it more dense than the water in my cup?
Nope. The water in both cups is the same temperature.
Wait, something to do with magnets? It's a trick cup of water.
Nope. No tricks. But you were on the right track with density. There's something in my cup that makes it more dense than the liquid in your cup.
Salt? Oh, that is so a trick.
Well, it's a little bit tricky. The tank has a little bit of salt in it. The water in my cup had a lot of salt in it, and therefore it was more dense than the water in the tank. It sank to the bottom.
So then what was in my cup?
Nothing. Well, actually, fresh water, right? No salt in your water, so the water was less dense than the water in the tank, and it stayed on the top.
Simple enough.
So what we've learned from these two experiments is that temperature and salinity, how much salt there is in the water, can both affect density. Things that are less dense will stay at the top. Things that are more dense will sink to the bottom.
Give you $1 to drink it.
No,
I'll drink it for $1.
I'm sure you would.
Man, was there a sale at the aquarium store or what? Wait, are we poking more holes in cups?
No, no holes in cups. This one's going to be just a little bit different. All right? We've set up a warm tank of water. I put some ice over here on the side.
Mark, if you wanted cold water, why didn't you just fill the tank with cold water?
Well, because what we want to do is look at the process. That bag of ice is going to cool the water. As that water becomes more dense, it's going to sink to the bottom. Now, if the water is sinking to the bottom, it needs to pull more water in on the side. And if we use a little bit of dye and give it a lot of time, we may be able to see this process.
Okay.
So let's put some right along here.
Yeah. I'm already liking this more than the cups already.
And we're going to put a little bit over here in the center. Now what we're going to do is give this a little bit of time. So we're just going to leave it and come back in a little while. Okay?
Sounds good. Check that out.
It's essentially a current being driven by differences in density.
It kind of looks like a lava lamp.
Very good. It's very similar to that. The material is heated, becomes less dense, and floats to the top. As the material cools, it returns down on the sides.
So put it all together for us, Mark. What does all this have to do with the Gulf Stream and climate?
Well, for that, we're going to need a map. It just so happens I've got one right over here.
I bet you do.
So, the Gulf Stream is part of something that we call the thermohaline cycle.
See, I told you it was a big word. Now, Mark, can you break that down for me?
So thermo, meaning temperature, and haline, meaning salt. These are the two factors that affect the density of water and therefore drive the cycle. In the Atlantic Ocean, there are a couple of places where the saltier, colder, more dense water takes a dive up near Greenland, Norway, down in the Antarctic, and it pulls in, just like in our experiment over here, the warmer water in the top surface. As the wind blows over the water, cools the water, that makes it more dense. But also, as the water evaporates and as the water begins to freeze out, it leaves behind saltier water. That also makes it more dense. Between these two effects, the cold, saltier water takes a dive and pulls in more water behind it.
Okay, Mark, now that makes sense, but how does it affect the climate?
Energy is picked up at the equator and carried to the poles like a giant conveyor belt. The air passes over the warm water, and the air that was warmed warms the land.
Okay, so that explains why some regions around here are warmer than we'd expect.
Exactly. Climate can be pretty complicated, and you need to understand the flow of energy to really understand the climate. And if you're trying to understand the flow of energy, you can't forget about these ocean currents. But most importantly, you don't drink anything that you think is Kool-Aid.
That just doesn't make sense to me. The Gulf Stream is just part of a worldwide system of ocean currents. In another 500 or 1,000 years, water that's on the east coast of the U.S. could resurface in the middle of the Pacific or Indian Ocean, carried there by ocean currents. So if you have a message that you need to send in a bottle, you should probably do that now. I'm sure it'll get there. Ocean currents. They may be down and dirty, but they're definitely science. I'm not getting it. You get it. It's not technically littering if it's intended as mail, right?
Kidding me? Oh
every time. Craig get the bottle. Craig playing poop. I'm done. I need a new job.